1.3, conditional statements. Now things are going to start to get even more interesting. A conditional proposition is a compound proposition which is in the form if P, then Q. I'm sure you have heard plenty of statements of this form in the English language or in another language, or probably in some of your programming classes as well, if you have taken very many of those. And the notation for a conditional proposition, oh wait, this should be conditional. That's what's happening here. So go ahead and correct that in your notes. It should say a conditional proposition, and it is denoted with an arrow. Sometimes it's denoted with a double arrow. In fact, that's how I learned it, so I might do that from time to time, but obviously it's just a little bit more writing, and it also is a little bit more cluttered. So either one of those is totally fine. And this is read if P, then Q, or we could also say P implies Q, and P is considered the hypothesis of this conditional proposition, and Q is considered the conclusion of this conditional proposition. And these can be a little bit tricky, and make sure that you're not getting these confused with either the conjunction or the disjunction, because otherwise we wouldn't need an additional kind of proposition. So let's take a look at this example. Let's say I told you, if tomorrow is sunny, we will have class at the beach. This is an example of a conditional proposition. The word then is understood, and it's okay to leave it, put it in, or leave it out, depending on how we are making the statement. We can put it in there for a little bit of clarity. When I was teaching high school geometry, one thing that we did is sometimes we would circle the hypothesis and underline the conclusion. And I think that that can be kind of helpful, especially when we're kind of new to all of this. So let's try to create a table for a conditional proposition based on this statement that I've claimed to you. So if tomorrow is sunny, then we will have class at the beach. So I've set up the truth table. Again, remember that anytime we have two propositional variables, those first two columns are always going to look exactly the same. It's always going to look like true, true, false, false, true, false, true, false. Now, let's suppose that we're talking about this first row. So let's say tomorrow is sunny and we have class at the beach. Yay! So was I telling you the truth when I made that conditional proposition to you? Yes, of course, that was a true statement. Now let's suppose tomorrow is sunny, but we don't have class at the beach. Well, then I lied to you, didn't I? So if tomorrow is sunny, it ends up being true, but we have class at the beach ends up being false. That is, we did not have class at the beach. Then my conditional proposition is false. Again, you can think of that as a lie. My original statement to you was a lie. Now, here's where things get a little bit tricky is, let's say tomorrow is not sunny and we had class at the beach anyway. Well, I didn't lie to you, right? I didn't say that we'll only have class at the beach if tomorrow is sunny. I just said that if tomorrow is sunny, then we will have class at the beach. If tomorrow isn't sunny, then basically all bets are off. If we have class at the beach, then great. I still did not lie to you, or in other words, I told you the truth. And if tomorrow is not sunny and we don't have class at the beach, then I also wasn't lying to you. In other words, I was telling you the truth. So, very important here, I'll also put a highlight around this, is to know the truth value of the conditional proposition P implies Q, or if P then Q. Pay attention to the results over here, is that a conditional proposition is only false if the hypothesis is true, but the conclusion is false. Otherwise, a conditional proposition is true in every other possible situation. Now, a conditional proposition can show up in several different forms, so I would like to practice kind of a little bit of variety over here. So all of these statements on the left are identical to, the conditional proposition if P, then Q. All of those are saying the exact same thing, just in a slightly different way. And let's go ahead and use the tomorrow is sunny, we will have class at the beach for our P's and Q's, so we can see a variety of how these are going to look. So of course, if P then Q, okay, we already wrote that down. We don't need to write that again. If P Q, actually that was the original statement. So that was the original statement, and then when we added the then, we saw that in there as well. Q if P. Okay, well Q is we will have class at the beach. So let's write that first. We will have class at the beach. Sounds fun, doesn't it? If, we don't really need a comma there, if tomorrow is sunny. And sometimes we have to change a tense here or there to make the sentence grammatically correct, and that's totally okay. Now, P implies Q. So I threw that in there earlier without saying too much of it, but this is a pretty common one, at least in mathematics, because when mathematicians have to say if P then Q, they have to say 4 words as opposed to saying P implies Q, and that's only 3. And mathematicians are notoriously lazy. I don't know about you. If we were to use our actual P and Q propositions here, it would say something along the lines of a sunny day tomorrow, try and squeeze it into the box, implies class at the beach. Again, we can adjust the wording a little bit to make it sound grammatically correct. Now, here's where it gets a little bit tricky, so remember this part. P only if Q. P only if Q. So P is tomorrow is sunny. So tomorrow, only one M in tomorrow. Tomorrow is sunny only if we have class at the beach. That statement has the same exact meaning as our original statement that said, if tomorrow is sunny, we will have class at the beach. Now, of course, we can't really determine what the weather is going to be based on having class at the beach. So if you'd like, you can take another look at the example in the zyBooks, which says something about you mowing someone's lawn and getting paid. And that particular statement sounds a little bit more correct, but this is still right in terms of our statement, P implies Q, or if P then Q. It's the same as P only if Q. Here are some other words that come up often: sufficient and necessary. Okay, so P is sufficient for Q. The hypothesis is sufficient for the conclusion. In our particular case, this would be written, a sunny day is sufficient, or you might say good enough, sufficient for class at the beach. Q is necessary for P. That's saying that the conclusion is necessary for the hypothesis. So this might sound funny, but it says having class at the beach is necessary for it to be a sunny day. And that's how we rewrite the same statement in different forms. A couple more things related to the implication P implies Q, or if P then Q. Sometimes we talk about 3 other ways of rearranging P and Q that have different meanings, or are they? The converse is the propositional statement Q implies P. And this is something that comes up a lot in mathematics when we say things like, okay, here's a theorem about mathematics. If a quadrilateral is a rectangle, then the quadrilateral is a parallelogram. I used to love geometry. Well, I still love geometry, just haven't talked about it in a lot. However, the converse is not necessarily true. If a quadrilateral is a parallelogram, then it is a rectangle. That is not necessarily true. So we're going to talk more about implications and their converses, but this is a pretty important vocabulary term that will come up as we're doing more logic statements and also when we get to proofs. I'm going to skip a little bit of space. The contrapositive is also a pretty important one. If you remember your high school geometry, you might remember the contrapositive to be not Q implies not P. So if not Q, then not P. And then finally, if you're just talking about if-thens and negations without doing, one negated and one not, then there's one item missing from this list, and that would be not P implies not Q. This is referred to as the inverse, and we honestly hardly ever use it. So I'm going to put that in parentheses because I don't want you to bother worrying about that. If you have a couple of homework problems, okay. I'm not ever going to put this on an exam because, again, it hardly ever comes up in my experience, but if you ever need to know it in the future, you can easily look it up and say, oh, okay, that's the inverse in case you need it. The biconditional operation is hopefully not too surprising. It says that if P and Q are propositions, the proposition P if and only if, I guess I could have made that line a little bit wider, is expressed with the biconditional operation and is denoted as follows. So with a double-sided arrow, and this can also be read, or it can also be written as P if Q, okay? But we read P if and only if Q. Oh, and I forgot that because I was running out of so much space. So that says P if and only if Q. Sometimes it's helpful to remember that this is saying the same thing as P implies Q and Q implies P. That's what the biconditional statement is, if we need to break it up like that. So if we were to create a truth table for the biconditional operation, start off with the simpler part. So true, true, false, false, true, false, true, false. Okay. For now, it might be helpful to just kind of tack on a little bit of a helper referring to this equivalent expression up here. So P implies Q, we know how to do that. Q implies P, we know how to do that too. It's just the truth values in opposite order. And then to put them together as an and statement, we just look at the previous two columns instead of going all the way back to the beginning. So Q implies P. So I encourage you to pause momentarily and fill out these two columns here. We should be able to do that based on what we've talked about so far. Okay, hopefully that was enough stalling and you did actually give it a try, and it shouldn't be too terribly surprising. Remember, an implication is false only if we have true implies false. So for P implies Q, that is only false for the second row, and it's true everywhere else. And then kind of reading from right to left, Q implies P is only false for the third row, true implies false, and it is true everywhere else. Now, in order to complete this last column, you can pause here too, but now we're referring to the previous two columns instead of looking way back here in the beginning. So we've already talked about conjunction, this and statement. So the and statement means that both statements have to be true. So we've got true, true, false, true, false, true, false, that conjunction is false, and true, true, is true. And since that is equivalent to P if and only if Q, that gives us our truth table for the biconditional statement. So I think it's helpful to have that in your notes so you know where it came from, but the punchline is this part of the truth table here, is basically observe that P if and only if Q is only true if both of the truth values are the same. And this concludes section 1.3.